This is the advanced functions lesson on transformations of cubic and quartic functions. Cubic is a degree 3, quartic is a degree 4. So let's take a look at what those graphs look like.
Here we have the cubic function. I'm doing this on Desmos. Now when I put a d value in, it shifts to the right 2 units, just like we would expect. So if I take that off and I just show you the d value here, this is just how the d value affects the parent function. Any function moves it left to right. Okay. So now what if I put in a c value? So the c value right now is 1. So it's lifted it up 1. Let me put this d value back to 0. Okay, here is, so I set that back to 0. So we've got still our shift 2 units to the right, but now we're adding on a vertical shift. So we've shifted 2 units to the right, that was a d value, and now we've added on to that the c value, which is lowering it and raising it. All right, let's get rid of that one. So here's a function with, it's been shifted, the cubic has been shifted 2 units to the right and 1 unit up. So what was kind of the turning point, or it's not really a turning point, it's more of a point of inflection here at 0, 0, the center of the cubic graph, that was at 0, 0. It's now here at 2, 1, because that's our new vertex. If you want to think of it back the way you learned it in grade 10, if this were vertex form, your vertex would come from these 2 numbers. It's the same thing here. The center of your graph is now moved over here. How about an a value? So an a value, of course, is a vertical stretch, vertical compression, and vertical flip. So that's changing your parent function, the cubic function, like that. And now I'm going to bring in a k value. So our parent function is in red, no transformations. The purple one is at a transformation of 2 units to the right, 1 unit up, a vertical compression of 0.5. See how it looks kind of wider because of the vertical compression of 0.5. Now I'm going to bring in a k value. So remember, k is a horizontal stretch or compression. The bigger the number, the greater the compression. So the greater the k value, the more compressed it is. And then if it's a fraction between 0 and 1, it's a horizontal stretch, and then we get a horizontal reflection. So there's your k value. Well, here's what the graph looks like with all of those transformations in it. This last red one here, that's darker red, that has all the transformations. This form you're looking at is sometimes called transformed form, or in grade 10 you called it vertex form when we had a parabola that had a vertex, because the d and the c value gave you the vertex. That's not, doesn't transfer to cubics, but it sometimes helps you to keep track of everything. The same thing, I'm going to show you quickly the same thing with a quartic. So here's the parent function for the quartic. And here it is in vertex form or transformed form. We're using transformations over 2 units and up 1 unit. So the vertex, when we're in this form that we're using today, it's not factored form, it's a transformed transformation form. We won't have the W shape that we get with a quartic sometimes. We're just going to have the flattened parabola. So it's got a vertex here was 0, 0. Now the vertex is here at 2, 1. If I add on a vertical compression, that purple is a vertical compression of 0.5, and onto that I'm going to put a horizontal compression of 4. So that's what your final graph would look like.
Example 1. Describe the transformations that were applied to the parent function to create the graph below. Then write the equation of the transformed function. So since today's title is only cubics and quartics, you should be able to tell by looking at this that it is the parent function was a cubic. So let's just, we don't need to, but let's just draw the cubic function on there. the cubic function has a vertex at 0, 0. Sorry, I shouldn't call it a vertex. It's not a vertex. It's the center of the graph. It's a point of inflection. And now we're talking about x to the power of 3. So let me just write that down here. I'm trying to graph y equals x cubed. A few values on there. You sub in a 1, you get out a 1. You sub in a 2, you get an 8. So we're just going to put a few points on here just to see what the graph would look like. If you sub in a 3, you would get a 27. I can't fit that on, but I can put it sub in a -1 and also get a -1. So we have this parent function cubic, which kind of looks like this little saddle or bend right here, and then up it goes back through this point, and then on to infinity. That's what our parent graph looks like. Y equals x cubed. So we should have arrows at the bottom there too. There's our parent graph. It's a little shaky, but that's what it's supposed to look like. So here's the form, the new form that we are talking about today. You can think of it, if you want, as vertex form, because it's very similar to that quadratic form when this was a power of 2 that we did previously in grade 10, where your vertex would be D and C. But all our functions don't necessarily have a vertex anymore, so you could kind of think of it as a center point as opposed to a vertex. But we're doing this is using transformations, because A, K, D, and C are very clear here in this form. When we're in standard form, you can't tell what the transformations are, but here in this form, I can see what all the transformations are. So first of all, okay, it says describe the transformations. So we've got a vertical reflection across the x-axis. So A is going to be negative. So vertical reflection across the x-axis. So look at my red graph here. It's flipped down now, so a vertical reflection would be kind of where I'm highlighting here. That would be a vertical reflection. Well, how do you know it's not a horizontal reflection? Because this function has odd symmetry, meaning the vertical reflection and the horizontal reflection are the same. Why are we saying there's a vertical reflection across the x-axis instead of saying a horizontal reflection across the y-axis? The reason for that is it's usually easier to think of determining the A value as opposed to the K value. So when we have to, you'll see this in a minute. Well, let me go ahead. So we'll come back to that point. The next one, see this kind of vertex point at 0 is now here. So I'm going to put a dot right there. I'll put it in black. This is where our new kind of center point is right here, or vertex, right here. So that tells me what my D and C values are going to be. So this center point of inflection right here on my cubic has gone over 4 units and up 5 units. So we've got a horizontal translation 4 units to the right, and we have a vertical translation 5 units up. So we know what D is and we know what C is. And this is what I was talking about before. We have different options because of symmetry. It's always easier to find an A value than a K value when we're looking for our own equation. And that's what the question says, write the equation. So in questions like this, unlike sinusoidal, for example, where your amplitude is very different from your period, for this function here, the cubic function, the A and the K value, when you're just looking at a picture, you can't tell if it was a vertical stretch or horizontal compression. So we're just going to let K equal 1, and we'll find a value for A. We're going to check for an A value by subbing in a point. So we have all this so far. The K, remember we changed it to a 1. So we're going to sub in 3, 6. So this is the X, this is the Y. I always put these in. It's very common for students to mix up where they sub numbers in. 6 equals A bracket 3 minus 4 cubed plus 5. So I'm going to do a few steps in 1. I'm going to bring the 5 over here, -5, so that's going to be a 1 equals and 3 minus 4 is negative 1. Well, I'll write that out. Okay, negative 1 cubed is still negative 1. So that's a negative 1a. Divide both sides by negative 1, and we get negative 1 equals a. So that's our a value. And our final equation on the bottom, f of x equals negative x minus 4 cubed plus 5. Don't forget it is a cube. We're really used to putting a square there from past years. It's very common to want to just make that a square, but this is a cubic function. And you can check. You can pick another point that we were given several points here on the black curve. We can pick one of them, a different one than what we used here, and sub it in and see if we get left side to equal right side. I'm not going to do that, but that's just a tip that you can do. Our second example is about transformations applied to the quartic function. So the last one was cubic, this one's quartic. And today, remember your title, we're only doing cubics and quartics today. And we are going to graph this when we're done. First thing I notice about this bracket right here is it's not set up properly. Do you know what I mean? We have to factor the k value. It's got to be in this form. See how the k is isolated, it's factored, it's divided away from this x is isolated. So we have to do that, and then we can state the transformations. I've done that here, and you can check it by distributing. If I distribute the 1/2 times x, I would get 1/2 x. Distribute 1/2 and multiply it with negative 6, and I will get this negative 3. And the exponent is a 4. So now that we have that done, we can describe the transformations. Let's start with the a value. The first one, that's a vertical stretch and a vertical reflection because of the negative. And the next one is a k value. That's a horizontal stretch by a factor of 2. It's always the opposite of what you think, the k value. You think the 1/2 is going to make it smaller, a compression, but it's a stretch. This one's also the opposite. It's a -6. You think that might be 6 to the left, but you know from years now that that means 6 to the right. So anytime you're doing any transformations horizontally or with the x, it's kind of the opposite of what you think it might be. The last one is straightforward. It's a vertical translation 4 units up. So we've described all the transformations. The question didn't say in order, but in order, remember, you have to do multiplication and division before you do addition and subtraction. Now we have to graph the function. Quartics in this form will have a U shape, so we don't have to worry about the extra kind of bumps and turning points that the W or M shape have when we have a quartic. These ones only have a U shape. The vertex will be at 6, 4, and I know that from here, 6, 4, so I know that about the graph. There are lots of different ways to graph transformations. The one I'm going to do is the one that students most often request when I'm doing graphing. So to find some other coordinates, we're going to set up this little coordinate equation. So what we do is we're going to take the x values from our parent function. This is our parent function. We're going to take x values that are on the parent function. We're going to divide them by k. In this case, divide by 1/2, which is really multiply by 2. And we're going to add d, which in this case would be add 6. Then, to find out where our y values are going to go, we're going to take our y's from here, from our coordinates from our parent function. We're going to take the y values. We're going to multiply them by the a, which is this -2. So we're going to multiply them all by -2. And then we're going to add on the c value. In this case, it's a 4. So I've kind of set this up in a chart. It looks like a table of values, but it's not a table of values. Here's some parent coordinates. You could write as many as you want. I just got these by subbing in numbers. So I sub in a 0, I get out a 0. When my input's a 1, my output's a 1. When my input's a 2, my output's a 16, and so on. You can do as many as you want here. This is that little coordinate equation we just talked about right here. I got all of these pieces from my transformed equation, my equation in transformed form, and this little formula here. So this is my x divided by k. My k is a 1/2. So x divided by 1/2 is 2x. That's where this 2x comes from, and so on. So let's get some numbers to put in the chart. So I'm going to substitute in. I'll show you all the steps here for a few of them. So the first, so I'm getting a new coordinate 0, 0. I'm trying to find out where that goes. So I'm going to end up with a new coordinate when I'm done. That's why I need the brackets. So the first thing I'm going to do is 2 times x. Now here's my x. 2 times x is 0. Let me write it out. 2 times 0 is my first step. Then I will add 6. That'll be my new x value. My new y value will be negative 2 times 0. And then I will add 4 to that. So this coordinate is really going to be 6, 4, which is the vertex. That's the y, sorry. So the vertex on my parent function was 0, 0. Now it's been transformed to 6, 4. Let's see where 1, 1 is going to be transformed to. So I'm going to do 2 times 1 and then add 6. That'll tell me my x piece. For the y piece, I take negative 2. I multiply it by my y. This is my y here. It's another 1. Y. xy, 2 times 1, negative 2 times 1 plus 4. That one is going to land at 8, 2. So the point 1, 1 is going to get transformed to 8, 2. 2, 16. Let's just do that without showing all the work. I'm just going to do it out loud. I take the x value of 2, multiply it by 2, that's a 4, add on 6, 10. I take the y value of 16, y times negative 2 is negative 32, add 4, negative 28. That's my new coordinate. And then where does negative 1, 1 land? Negative 1 times 2 is negative 2, plus 6, 4. 1 times negative 2 is negative 2, plus 4 is 2. Now that I have all of my coordinates, I did that first because now I can figure out where to place my axes. When I think about my where I want to set up my grid and what scale and everything I want to use, I probably won't graph this one. Negative 28 is just too big, and even this number on the parent function, 16 is a pretty big number. Probably won't. I'm not going to graph this one, but using my other coordinates, I set up my x and y axes, and then we put all of our points on and draw the graph. So why don't you press pause and work on that, and when you come back you will see the finished graph on here. I've got my points on there. I couldn't fit any more on. Now I can kind of figure out where it's going with that other big coordinate I have, 10, negative 28. Remember, when you make the curve, don't make it a real U shape, as curved a U shape as a parabola is. We're going to try and make it a little flatter than that. There's my graph. Important points on here that we're going to talk about in the next example are the x-intercepts, finding where the x-intercepts are. It's always important, you know this from grade 10 with parabolas, always those x-intercepts can be really important. You want to know, for example, when will the ball hit the ground or something like that, all those zeros. So right now I just guessed. Right? All I had were these 3 points, so I just drew a shape that looked like a quartic. But in our next example, we're going to get a little bit more information. Example 3, determine the x-intercepts of this function. Notice that the vertex of this quartic is 4, negative 32, and it opens up because of the positive 2. So I know that it's going to have, let me just do a little sketch for you here. If the vertex is at 4, negative 32, that's way down here somewhere. So let's say that's 4, negative 32, and it opens up, and it's a quartic in transformed form, so I know it's not going to have that W or M shape. It's going to look like this. I know it's going to have 2 x-intercepts. The x-intercepts occur on the x-axis where our y value is 0. So the math that we're going to do is we're going to let f at x, that's this piece right here, we're going to turn that into a 0. So there we have our equation with a 0. Next thing we have to do is we're going to have to isolate x. This x right here has to be isolated using SAMDIV. That's the opposite order of bedmass. Remember, when you're isolating, you do subtraction addition first, not last. This form is the easiest way algebraically to find x-intercepts. since x needs to be isolated and there's only one x, there's just one x right here. Oh, my mouse is sticking. One x right here. Unlike factored or standard form. So factored form would have a couple of brackets like this with various x's in them. Standard form would have possibly 4 x's in them. They're hard to isolate. So when we're in this form that we're learning today, the transformation form, it's much easier to find the x-intercepts. So let's start with bringing over the 32. Remember, subtraction addition first. So I'm going to add 32 to both sides here first. Add 32, I get 32 equals 2 1/3 x minus 4 to the power of 4. What's the next step? So I did the subtraction and addition. That piece is done. Now I'm on multiplication division. So it's actually not division, but it's not multiplication, but it's division. So I'm going to divide this whole side by 2. And divide this side by 2. These 2's will cancel out, and I'll have 16 equals 1/3 x minus 4 to the power of 4. Okay, now what? Look back up to your order of operations. We're on exponents next, E for exponents. So I have to get rid of that power of 4. To get rid of the power of 4, the opposite operation is the 4th root. So I'm going to put a 4th root here and a 4th root here. So this 4th root kind of cancels out this 4. So on the left side now, on the right side, sorry, what I have is I can drop that outer set of brackets, 1/3 x minus 4. What do I have on the left side? So when you have to draw in your own square root sign, because there wasn't one in the question, you have to, if it's an even number like this, a 4, you have to put the plus or a minus, just like if it were squared. So if I had the square root of 6, or just the square root of 9, that's plus or minus 3. So if I had, on the other hand, the third root of, say, 8, the third root of 8 is only a positive, because -2 times -2 times -2, -2 cubed is not equal to positive 8. So when you have an even exponent, you need both. When you have an odd exponent or index, radical index, you only need one. So this 4th root of 16 is 2, but I've got a plus or a minus 2 here on this side. So we have two solutions because we have a plus or minus, just like when you would do the quadratic formula, x equals -b plus or minus the square root, because you get two roots, right? We're going to get two roots. We talked about that already when I did a little sketch. We're going to get two roots, two x-intercepts, two zeros here. So I'm going to write this out twice separately, just so we do this for the first time carefully. So we've got positive 2 is going to equal 1/3 times x minus 4. And, or we'll put and, we're going to have also -2 is equal to 1/3 x minus 4. The whole and versus or is another discussion that we won't have right now. So I've got two different solutions, positive 2 and -2. I'm going to isolate, let's start with the positive 2. So I'm going to multiply this whole side by 3. To get rid of that 1/3, which means I have to multiply the left side by 3. So these are gone, and I have 6 equals, drop the brackets, x minus 4, add 4 to both sides, and we have 10 equals x. There's one answer. Now let's go over to the other side. I'm going to do the same thing to get rid of that fraction in front. I'm going to multiply both sides by 3, or divide both sides by a third. Multiply this by 3. That gives me -6 equals x minus 4. And then we're doing the same thing. We're going to add 4 to both sides, add 4. And we have negative 2 equals x. Negative 2 equals x. So that means the x-intercepts are, therefore the x-intercepts, our x-intercepts are at x equals 10 and x equals negative 2. So you would have 2, 1 at 10, 1 at negative 2. And that's how you find the x-intercepts. Now you have more information to use to graph a quartic function, because you could now add on the x-intercepts. It requires a bit of math, and it doesn't always work out to be nice even numbers, of course. We get all kinds of irrational numbers and decimals, but that's how you find the x-intercepts. That's it. You're ready to go, and you're ready to work on your homework for today's lesson on cubics and quartics in transformed form.